Hey everybody, today we're starting to talk about optimization. Optimization is one of the things that calculus is really good for in the real world. The downside of that is that when we study it in Calculus 1, we're doing a bunch of word problems. In this video we'll do an entry level one. In future videos we will get to some more difficult stuff. Let's go. So we have a technique already for finding absolute extrema for known functions, the closed interval method. If you've got a continuous function and a closed interval, then you're definitely going to have an absolute maximum and an absolute minimum. They can only occur at endpoints or at critical values. So here's the problem we're going to do in this video. A rectangle sits on the x-axis and two of its vertices lie on the graph of y equals 4 minus x squared. What's the maximum possible area of such a rectangle? So, of course, the first thing we want to do is to sketch that parabola and the rectangle. So here we go. Good general rule whenever you're doing a word problem is draw a sketch if you can. So there's lots of different ways I could have drawn this rectangle. I could have made it narrower and taller. It's pretty clear that if you do that, if you make it too narrow, you're going to get very, very, very small area. Similarly, I could have made it very wide and very thin, and if I had done that, I could have also made the area very small. So I expect an optimum somewhere in between. We just don't know exactly where. Next, and this is true for all word problems, we want to try and write an equation for the thing that we want to optimize. And to do that, we have to choose variables. The choosing variables and writing an equation really go together. So here, I'm trying to optimize the area of a rectangle. So length times width or base times height. That's the equation I want to make. In terms of variables, since they already gave us 4 minus x squared, I'm going to pick my variables to be x and y, where x comma y is a point that lies on this graph. In particular, I'm going to restrict that point to be to have to be in the first quadrant. You can see that if I make x negative, I still get the same rectangle there, so there's no point in considering that. Also, the way the problem is phrased, the rectangle needs to sit on the x-axis. We're going to keep the rectangle above the x-axis. Overall, the area of the rectangle in terms of those variables is 2xy. That's the thing I need to optimize. The problem is that in Calculus 1, we're only able to optimize functions of a single variable. So 2xy is not good enough for us. We got to get the y out and some more x's in. Fortunately, x comma y lies on this parabola, so I can take out the y and put in the equivalent 4 minus x squared. So that's what I'm doing in this equation here. Simplifying a tiny bit, I get that the area is 8x minus 2x cubed. So you give me any x value, and that'll give you back, I'll give you back an area of the rectangle. There's one thing we have to do before we can start differentiating, and that is to find the domain. What x's are legitimate to plug in here? You really have to do this on any optimization problem. Here, for example, we want to use the closed interval method, so we got to make sure our domain's a closed interval. The fact that x comma y is in the first quadrant limits us right away. So x can't be negative, and it can't be bigger than 2. So the domain is going to be 0 to 2. Notice, by the way, that that area function I wrote on the previous slide, just as a pure function, has domain all real numbers. But as a model for the area of this rectangle, it has domain 0, 2. So you do have to take into account the real-world considerations when you consider the domain, not just the formal algebraic structure of your function you're trying to maximize or minimize. Okay, now we're all set to do that closed interval method. We want to find critical values that are on the interval 0, 2. So we differentiate, we set equal to 0. I get 8 minus 6x squared for the derivative, set it equal to 0. Move the 6x squared to the other side, divide by 6 to get x squared equals 4/3. Take a square root and get x equals plus or minus 2 over the square root of 3. I'm not bothering to rationalize denominators. That's not something that matters so much to me. It's kind of an artifact of times when dividing by radicals was a lot harder than multiplying by them. But obviously that's not an issue anymore. Now, only one of those two roots lies in the domain, right? We're looking from 0 to 2, and so the negative root there is not in our domain. We're going to ignore it. We have one critical value, 2 divided by the square root of 3. So there are three possible places where an absolute max can occur. X equals 0, x equals 2 over root 3, and x equals 2. I plug all three of those in, and clearly the largest of the three is at x equals 2 over the square root of 3. And I got area of 6.2 units, 6.2 square units. So the area is maximized when x is 2 over the square root of 3, and the maximum area is about 6.2 square units. Before we complete this video, let's just run through the process, because even though optimization problems are all a little bit different from one another, the general process is pretty much always the same. So start by drawing a picture, see if you can get a visualization of some sort to help you understand the optimization problem. Next, you want to select variables and write a function for the thing you need to optimize. At first, it's okay if that function has more than one variable in it. But in your next step, you're going to have to reduce it to just one variable using substitution. Find the domain of the function you're trying to optimize. This is essential. It's something that's frequently left out by beginners on these problems. Apply the closed interval method. Find all of the critical values that lie in that domain, and then plug them into the function. Also plug in the endpoints. The largest of those values is going to be the maximum. The smallest will be the minimum. If the domain is not a closed interval, then we're going to need another technique. We're going to get to that in the next series of videos.